this. All right, let's get started. Okay, so today we're going to go more into neural networks, and as always, reminder, please ask questions. So, neural network. A neural network is a computational model inspired by the human brain that processes data through layers of interconnected nodes to recognize patterns and make predictions. Okay, first of all, to understand what a neural network is, a neural network is made out of many neurons. And all a neuron is it's something that holds a value. So it holds a piece of information. That's all a neuron is. And each neuron holds a grayscale value between 0 and 1. So 0 being uh, not accessed by the image or completely black, or 1 being activated. That means it's activated. So who can tell me what they think this image they see here is? What image do you guys see here?
Number 3.
Yeah, it's a 3. Yeah, so that's what it is. And if you noticed that all the white values is exactly 1, all the black values are 0, and anything in between that, like a smudge or the edges that are not exactly straight, it's a value in between that, 0.6 or 0.5. So that's all a neuron is. It converts it into grayscale and then holds this value between 0 and 1. All right, let's go. And since this is a 12 by 12 image, uh, pixel image, it has a total of 144 neurons. Okay, so this number represents its activation. So 0 and 1 represents its activation here. So like we were talking about yesterday on the activation of this, um, each of these represents the activation. So 0 being it's not activated, and then 1 being this neuron is activated. So let's like learn more on what that means. So here I'm gonna start with the output layers. So if you notice, we had 144 neurons in total because we had a 12 by 12 diagram of the image, right? So if we now put this into the input area, you notice that there's 144 one of these neurons in that one area. So that's how it's going to be. So this is going to be 1, 2, dot, 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 143, 144. So there's going to be 144 neurons in the input layer. And if you look at the output layer is the final outcome. So it's going to tell you whether the number, so in this case, we're making a neural network that can differentiate between the number 3 and 5. That's the goal. And now, based on some values in the middle, it's going to tell us if the outcome is either a 3 or a 5. So, how that works is it uses this probability kind of thing. So, it checks how much the system thinks the image is given that it, okay, how much the system thinks the image given has the probability of being that given number. What that basically means in simple terms is after taking this input data, let's say it's taking in uh, an image of a 5, right? The output would tell you the probability of it being a 5 and the probability of it being a 3. So in this case, what is it? 0.8 value, which is an 80% chance, right? Of being a 5 and a 20% chance of being a 3. So that's how neural networks works on the output side. It gives the model a probability of it being a certain number. And now we're gonna learn how it works, how we can optimize that, how it comes up with this probability and different things like that. So in between we have these hidden layers over here. Let me go. Okay, sorry. It's glitching. All right. So based on the image given, it's going to activate different neurons in the hidden layer. So for example, we have an image of a 3 right here, right? And now it's activated some of these different middle values. So in this case, it activated this, it activated this, and it activated this, and this, right? But let's say, for example, we have another data set, right? Let's say it's a 5, right? It's going to activate some other values. Now it's activating these values here. These, oops, this. Okay, so it's activating different of neurons based on the image. And how this works is that in this given image, it breaks down this image into different components. Let me show an example how it breaks it down. So in this example we looked yesterday, right? We take this image of this jack-o'-lantern, it then breaks it down into its raw pixels, and then it looks at, in the early stages, in the early layers, it's going to just extract all the edges. In the middle layers, it's going to take all parts of the object, and in the deep layers it's going to take a high level summary. So let's see how this looks in the neural network. So going back to this neural network, let's start with this. Let's start with 3, actually. It's a little bit easier to understand. So let's say in these first layers here, what it's going to do is it's going to look at certain things on the neural network. It's going to first understand the shapes and edges of these two images. We have threes and we have fives. So let's say it understands a curve of it. So it's going to draw out a curve. In another one, it's going to take one other thing and it's going to draw that curve. Then it's going to understand this shape and it's going to draw that shape over here. So it keeps creating these types of things. And what it does is after you give the pixel, so let's say you give it that one pixel, and now it's checking which which of these curves that these pixels match with. It's then, okay, it matches with this one. Okay, let's go on to this layer. Then it activates this layer. Now this layer is activated. After this layer is activated, it activates these other ones and then it checks, right? This one is also activated here. So then, oh, look, these curves are similar. Then it goes on to the next curve. Then it sees, oh, wow, this object here is similar to that pixel. Then it becomes activated. So that's how a neural network works. It it activates different components. It breaks down the image into different small components, and then it activates different layers. So, for example, it breaks this image down into this part here, this part here, this part here, and this part here. And then it checks where are these curves present in the neurons, and then it makes a prediction based on that. So that's how these neural networks really use these curves and break down these curves to understand what the output or the prediction would be. Okay, let's go on to the next. Okay, so over here, the networks, yeah. So like I was saying before, the network then breaks down the two types of images, so in this case 3 and 5, into the components, and for each neuron, it represents a different component, and it activates it based on the similarity. So it breaks down each of these neurons into a different component, and then it activates them if they're matching. And if they're matching, it activates and makes a prediction based on it. It's looking at how many of the matching features, and it's creating the probability based on that. So let's understand this a little bit more using math. So if you guys remember, can you please explain the layers part for the image? Okay, layers part. Okay. Okay. So are you saying I'm trying to understand your question. Is it the part where I'm talking about how the neural network breaks it down, the pixels and stuff? Is that the part? In this slide, yes. Okay. Yeah, okay. Right. So basically what it does is the is there any questions? Okay. So let me break it down. So each one of these pixels that you see on the screen is a input neuron here. So this input is here, 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 right? So let's say we have a 0, we have a 0, we have a 1, blah, blah, blah. We have it for 144 because we have 12 by 12, right? So we have 144 neurons over here. Now, over here, what this is it basically breaks down the image data set you give it, right? It's breaking it down into its components. What that means is that it's extracting. Let me go back a slide so it's easier to understand. Go back. Okay. So what it does, sorry, what it does is it breaks down this components. So right here we have a jack-o'-lantern image. It first converts it into its pixels, right? Those are the neurons. It's creating the neurons. And then in its early layers, like so a layer is basically these different columns, I guess you could call it, of neurons. So there's a layer here, there's a layer here. In this case, there's only two hidden layers. Okay, that's how I created this model. There's two hidden layers, and then in these two hidden layers, there is 6 neurons. Okay, and let's say in its early layers, or let's just say in the first layer, there it understands the edges completely. It breaks down the image into its edges. It's understanding this curve here. It's breaking down the curves like this. And then in the middle layers, it's understanding the parts of it. It's understanding this. It's understanding this. So, for example, the model is trying to make a prediction. It's checking, okay, does this neuron fit with this curve? If that's yes, it's gonna activate this neuron. So let's just say A is for activated. When it's activated, it goes on to the next check, and then it goes on to the next check until the neural network that you built is done, and it finally comes up with a probability at the end of what image it thinks it is. I'll explain more on the math behind it, so it'll make more sense. But does it make sense so far? What I'm saying? Mhm. Yeah. Yes. So, okay, let me explain more on how it works. So, right here, right, how it's understanding the curves and stuff, it calculates. I'll show like the math in a second, but it calculates, right? It's kind of checking, okay, it's seeing, all right, so there's kind of some gray scale, like gray values and pure white and pure black. That usually means that there's an edge or corner. Then it understands this and it's saying, okay, let's first understand this edge here. Let's understand this through map. Okay, this is the edge because there's some gray values as well as pure whites and pure blacks, and it's understanding that's the edge of the image, and then it's understanding some other features like that as well. Does that make sense how that works? Because it's looking at it through each pixel. That's how it works. It's looking at it through each pixel. That's how we're getting the values between 0 and 1. Okay, perfect. All right, cool. Is everyone good to move on? Does this make sense to everyone so far? Okay, cool. Let's move on. Okay. So now I'm sure you guys remember this example from yesterday. In this case, I had a neural network with 784 neurons in the input layer. And then it's trying to predict whether it's a square or a circle. So here, or in any neural network, the neurons are connected to the next layer through things called channels. And let's understand how we can calculate the values for these. So we can use this equation here. The value for this, the neuron, right, times some weight. So each one of these channels is going to have a weight. It has a value of a random weight. So what the neural network does is it assigns a random value for the weights. Everything is random. Let's say this could be 0.9, this could be 0.7. It doesn't matter. It's going to randomly assign a weight between some certain values. And after it assigns this weight, it's going to then improve itself. So because obviously with the untrained neural network, when it assigns some random weights, it's not going to be accurate, right? It's just going to be some random mess. It's not going to be the perfect model. So let's try to understand how this weights come to. So does it check? Okay. Okay. So if you guys remember that these neurons have to be activated, right? And we can't use any activation function um, because it needs to be squished between 0 and 1 because that's how activation functions are. If it's 0, it's not activated. If it's 1, it's not. It is activated. The closer it is to 1, it is activated. So to do this, we can use an activation function like ReLU or the sigmoid function. So in this case, I'm going to talk about the sigmoid function because that's the example I've been using in my previous classes. So if you guys remember how a sigmoid function is, right? It's this curve right here. We're going to be using this curve. So it's the curve from logistic regression for if you want a little refresher on that. So what it does, it takes your linear function and then it squishes it using the sigmoid function. So it takes in that linear function and it's just squishing it between the values of 0 and 1. And that's what this activation function uses. So it's using the calculation you did here for this, and it's using the sigmoid function to come up if this cell or this neuron should be activated or not. So that's how this works here. Okay. So since the output in this model is wrong, the model goes back and does back propagation and adjusts the values and keeps doing it again when the results are correct. So let's really understand how back propagation works and how this model knows what's wrong and right. So what it's going to do is it's going to, since in the beginning the values are, yeah. So like I said before, in the beginning, all the values are random and the model needs to improve. So we have to calculate this thing called cost. And basically, all cost is, it's taking this output that we generated, right? I've just made up some output values for now. So let's say the model prediction outputted for the value of 3 for this image here is 0.4. So it's a 40% chance of being 3 and 60% chance of being 5. Well, obviously, this is completely wrong, right? We have a 3 here, and it's obviously a 3, not a 5. And it's showing that 5 is the highest amount. And what the model does, it cross references to the actual result. Since you're training this model, it already has that data, right? It knows what's correct and not. So it checks and sees the prediction it made. Okay, I made a prediction of 0.4, but the actual result is 1. So it's wrong. So how can we adjust this? I made a prediction of 0.6, but the actual result is 0. How can I adjust this? So first, it sees the magnitude it was wrong by. So if we look at the cost function here, what it does here is it subtracts your model's prediction by the actual result. So in this case, 0.4 minus 1 squared plus 0.6 minus 0 squared. Okay, if you can remember it through this quick little formula I'm going to write down. Summation of prediction. So I'm going to say P for prediction minus actual squared plus, oh yeah, not plus. It's just that. That's it. That's your formula. That's all it would be. So if there was, let's say, another value, let's say it was 2, right? We're working with 2 data sets. Let's say this is 0.1, this is like 0.4, let's say, and this is 0.5. Okay. Now we would just do this for 3 times. We would add in 0.1 minus, let's say it was 1. Okay, just for example, you would add in that as well. So far, does this make sense on how we can calculate the cost of the neural network? Does that make sense to everyone? Okay. All right, let's move on then. Okay, so once we figure out the magnitude of how we were wrong with, we can also, okay, for example, the goal of this actually is to have the most minimum cost function. So what does this kind of sound like? Can anyone relate to what this sounds like? We're trying to get, the goal is to get the most minimum cost function. We've seen this before, right? It sounds really familiar. What else models goal is to have the most minimum what function? Anyone remember that function? For example, in logistic regression, the goal is to get the most minimum what function? Sounds, yes, right on. Good job, Sanjana. Yes, it's like the mean squared error, right? It's like the loss function. Same goal here. So in this case, the goal is to have the most minimum cost function in neural networks. So that's how this works. So the network is going to keep trying these random variables. Well, actually, it won't be random anymore. Only the first time it trains, it's going to be completely random. All the biases that I was talking about in the channels, it's all random in the beginning. But after that, it's going to adjust itself. It's not going to be just a random thing. So what it's going to use is this thing called back propagation. So back propagation looks at if these values need to be adjusted upwards or downwards and changes the weight to match that. So basically, here, if you notice, we have to go upwards, right? Because this is 0.4 and this is 1. So it's going to change the weights accordingly so it goes upwards. And then here, it needs to go downwards, obviously, right? And this is at a more higher weight. So basically, let me explain graphically because it's going to be hard to explain it mathematically. So I'm just going to explain it graphically how this works. So let's think of a graph, okay? And the goal of this graph is to find the lowest point. Of course, you can use calculus and you could find the lowest point, but it would probably not be the actual lowest point. There could be multiple low points in the graph, and you're trying to figure out which low point is correct, right? So if you're taking calculus, you've probably done something similar to this, but in this case, we're going to do something a little bit different. So the neural network is going to predict at, let's say, a random value right here, right over here. Then it's going to look at the points to the right of it and the points to the left of it. And then what it does, it checks, okay, the goal is to get lower. So are the points to the right higher or the points to the left higher? If the points to the left are higher, it's going to move this down a little bit. And then it checks again. It does another check. Okay, now I'm at this point, let's say. Okay, this is my first training phase. Now, where am I at? Should I go higher or lower? After looking at this, it does another check. Now it figures out it has to go lower. And let's say it goes here. Okay? Now we're in the complete opposite direction, right? So it looks at the slope, looks at all of these things, it checks which points are higher, and then it keeps on doing this training back and forth, until it optimizes its values until it gets to the correct answer, right? So that's how this kind of works, graphically at least. So far, does this make sense on how back propagation works? Oh, let me also show it this way as well. Let me show you on the neural network. Okay, let's go back to this example. So forward propagation is when we have our weights, we do our calculation, right? Our x, whatever x value here, multiply by the bias of each x. and then add in the bias of this, right? Okay, looks like we have a question. Let me see. So, what does the negative value cost such as? Okay. Oh, okay. No worries. I'll be sending out a recording, Farhan, by the way. So he can watch that. Okay, so Liam, to address your question, so a negative, let me look at your question again. A negative, okay. A negative cost would indicate it would go, let me show you. Let's go back to that. Okay, usually when it's negative, that means the model needs to go change upwards. It needs to go up more than it needs to be changed downwards. Does that make sense? Remember how I was talking here that you have to go, uh, depending on how you need to change it, you need to go upwards or downwards. So if it's negative, it usually says that you need to change your model where it goes upwards, basically. Does that make sense? Just trying to just so negative means need to go upwards. Yeah, yeah, no worries. Okay, perfect. All right. Where was I? Oh yeah, back propagation. Okay, so going on to back propagation, basically forward propagation, right? We add in the weights, we do the sigmoid calculation, check the activation, blah blah blah, right? Now we start here for back propagation. We get an output, we understand that there's an error in the output by some magnitude, and we know how to adjust it. So the model goes backwards this time and does the same steps, but now it adjusts these backwards, and then it does forward propagation to do all the steps again, and it's going to keep repeating that cycle over and over again until the amount of trials you set is done, or it can't be like improved any further. Usually if you have a GPU optimizer, you'll probably work with that stuff, but that's how it kind of works. Okay. Also, is the mean square error calculation as a cost calculation, or is it different formula? So it's going to be a different formula actually for this. The cost is actually easier to see. The mean squared error formula, it's a little bit different, but you don't need to worry too much on the formula end because the program is going to do it for you. But all you have to understand is how to understand your results, right? If it outputs out your cost, you need to understand, okay, I have this much of a magnitude. Let's see how I can improve my model, right? That's what you need to understand. But it's going to be slightly different formulas, but it has the same end goal, I guess. Yeah. Because this formula would be summation of prediction minus actual square. This is this formula. Okay. So moving on. Okay, so I'm not sure if Padma is on this call actually. Is he? No, he's not. Okay, yesterday Padma actually brought in very useful topic. He was talking about using an optimizer like Atom, and yeah, so this neural networks do use optimizers. So that back propagation, what we do is we take the gradients from that back propagation and we use it in an optimizer like atom or gradient descent. So it's taking, so the gradient, by the way, is just the magnitude of how much we need to change each value, right? Outputs at that value and it tells us how much we have to change it by. That's all the gradient is going to tell you. And then it takes those gradients and it does an optimizer. So the optimizer, what that does, it's going to optimize these weights. So in back propagation, it's going to change the weights based on what the gradient said when it did back propagation, and it's going to alter those weights, and then it's going to run the neural network again and then see the output. Okay, sorry guys. I just had to do something real quick on the screen recording since it's done. Okay, in this next step, um, I'm gonna just explain it now, but this is more on the code side. So whenever you make your neural network, there's gonna be this thing called max pooling that you need to set. And usually, for me, I set it to max pooling 2 out of 2. Basically, what that does, it creates a 2 times 2 window, and then in each position, it selects the highest value to make a more simple and downgraded version of the image, and it keeps only the most important features. So what this means, right? We have our image. Say we have the image from before, the 3 image, right? What it does, it creates a 2 by 2 window that looks at 4 neurons at a time, like this, this, right? It's looking at 4 neurons at the time. And what it does is so it makes the images more simpler for the next layer, right? Because remember the first layers are what? Very vague. It's only trying to understand curves and stuff. What it does, it makes the image simpler for the neural network to understand. So it takes these images, let's say we have these random values, it checks which value is the highest in each one. So in this case, what would it be? 8. In this case, it would be 8. In this case, it would be 8. And then it creates a new image using those high level values. So it's only going to take that value and it's going to keep it there and train that neural network on that. So that's how max pooling would work, and it's very important for to have in the code. So it looks at all 4 of these and then does that. So we're gonna get into the programming, but before that, does anyone have any questions so far on what they uh, they learned, or any questions about this? So here is a neural network I created for to predict between 2 types. Well, I'm predicting a rare cancer called adrenocortical carcinoma. It's a very rare cancer in the adrenal glands. But I'm creating an AI model here to predict the differences between a normal adrenal gland data set and a cancerous data set. So this was probably my first year project in doing it. So let me just go through the steps. So here I've loaded all my data, and all you really need to know from here is this: I'm just importing all my data and then setting a certain size. So if you guys remember, in my today we worked with the number 3, right? And the image was 12 pixels by 12 pixels. So what I'm doing here is I'm scaling all the images to a certain size. So in this case, I'm scaling all of my cancerous images to 224. If you notice here, 224 by 224. So in total, who wants to do the math real quick? How many neurons would we have in the first column? How many neurons is that? Did anyone do the calculation? No, it's fine. So that would be 224 times 224. That would be, yeah, 50, around 50,000 neurons. So imagine all of these circles are neurons. I have 1, 2, 3, 4, and then 50,000. That's how many neurons would be in the first image. And the reason I have it super big is so the neural network's more complex and can understand more clearly the exact regions of the tumors. Okay. Here I performed this step called data augmentation. And data augmentation is very important because what it does is it transforms your data set into a stronger database. Basically, in any type of machine learning project, um, don't worry about the code too much because this is very advanced code, but I'll be showing simpler code tomorrow. But basically, what data augmentation does is it transforms your basic data set that you have. Let's say you have some images, right? Cancer, blah, 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 right over here. And what it does, it transforms it into a more complex database. It scales the images by a certain amount. It shifts the image by a certain amount, right? It's just creating a more diverse database so the model can understand any type of data. So even if I give a data that's slightly altered, it'll be able to accurately understand the exact regions of the tumors instead of focusing on other classification features, like maybe a dark spot, right? Even if that's not a tumor. That's what it's going to do. That's what data augmentation is. So far, anyone have any questions? No? Okay. Okay. So here in my code, I'm just setting up all the metrics needed. So don't worry about these too much yet. Here I'm actually creating the model. So right over here, I'm using a couple of things, right? I'm creating the model and I'm using a already pre-trained model. And what that is, it's already a neural network that's been trained on some other databases. I'm just pulling that database in and feeding that with the images I got. So I'm feeding it the 224 pixels by 224 pixels, right? And then it's using the weights from here. So if you guys remember what the weights are, I'm just taking the weights from this other model already. So it's going to start off with some strong weights compared to just randomly generating the weights. So basically, in the channels, we have the weights, right? That is randomly generated in the beginning. So I'm just pulling in the weights from an already trained model. So the model starts off with a high accuracy and can improve faster. So that's what I'm doing here. And here I'm creating my actual model. So I'm creating the model over here. So let me go back to the simpler code that I created. Yeah. So here would be how you would create a model. So you would create the model by specifying a couple of things. So right here in my first layer, I've said that I want it to be a ReLU, and then I use the max pooling. And if you guys remember from what I taught before, the max pooling, all it is, it's making the model or the image simpler for the model to understand. It's only looking at the most important features, right? That's what max pooling does. So it can break down the model even more. And then here, I'm feeding in the input shape, and all this input shape is, in this case, I'm feeding in a image of 150 pixels times 150. That's all this is. And then this is just the size of the models I'm using. So it's going to get bigger, each layer 64, 128. That's all that is. Nothing too complex. It's just the size of the network I'm creating. So that's all this part. And I'm creating uh, multiple layers. If you notice, I have a first layer, second layer, third layer, and then fourth layer. And this flatten, what this does, it takes in my two-dimensional data and two-dimensional model, and it's basically flattening this into a 1D data set so the model can understand it. That's what this is doing. And then it's using ReLU here instead of sigmoid, right? Like I was talking before, and that's the activation function. So it's checking which neurons to say yes to and go to the next step, and which neurons to say no to and just stop there. So far, does this make sense on how I'm building the network through code to everyone? This is step makes sense because this is pretty important here. Okay. All right. So after this, I'm finally compiling my model and I'm using the optimizers here. So I'm using Atom and I'm using a loss function. In this case, binary cross entropy. You can also use mean squared error. And I'm taking in or calculating the accuracy. So that's the metrics I'm going to be using. And then here is where the training phase of the model is. So epochs are basically how many times I want this model to train, or how many back propagations I want this model to go. Remember, guys, that the model back propagates, does an optimizer, gets the values, and runs the model again, right? It keeps checking how much it was off by, right? It checks how much it's off by and then changes the values and goes back. So in this case, it would do it 10 times. That's what we're using here. Okay. And all this code is, it's just plotting some results. And then I'm just using a test data here and I'm checking the prediction of that. That's all this is. But this part of the code is the most important. The part where you're actually developing the model and the part where you're training the model. So far, does this make sense, everyone? Anyone have any questions? Okay. Yeah, so tomorrow, then, oh, we got a question. Nice. Could you please let me know the reason why generator is used to... Okay, so basically this code is just creating a bunch of test data because I didn't actually collect any data, so I just created a generator that would just create some test data with some test, you know, pixelated images with this type of scaling and different things like that. So that's what I mean. This is just test data, so you guys don't need to worry about this right now. Tomorrow, I'll bring in an actual database and then we'll work with it tomorrow. Does that make sense? Okay. Yeah. Okay. Yeah. Anyone else have any questions? Okay. Yeah. There's nothing else. Okay. So today we're gonna go over neural networks again. Who wants to tell me what they remember from yesterday on neural networks? Can be anything. Or just like what a neural network is on a high level. What's it close to? What part of the human body is it close to?
The brain.
Yeah, the brain. Yeah. Okay. Okay. Cool. So so by definition, a neural network is a computational um, is a computational model inspired by the human brain that processes data through layers of interconnected nodes or neurons to recognize patterns and make predictions. Okay, so what does this mean? Right. So a neuron is something that just holds a value. It holds a data value between 0 and 1. Okay, we'll learn more on that in a second. Each neuron holds a grayscale value between 0 and 1. Okay, and this image here, we have a 12 by 12 pixel image. And that means in total, we would have 144 neurons. And what a grayscale value is basically it takes an image, it could be any image, and it converts it into a grayscale, and then it looks at each pixel and checks the grayscale value of that pixel. So, for example, if it's black, it would be a grayscale value of 0, and if it's white, it would be 1, right? And these grayscale values represents its activation. Okay, this kind of triggers in the code like which neurons are activated and stuff like that. We'll get more into that in a second. But I'll give you one example. For example, right, we're predicting the number 3 because this is the image of a 3. And let's say that the how it works is the image, it kind of understands the pattern of where the whites are. It starts to understand, okay, I see that there's a majority whites here that are forming some type of pattern. So it starts understanding this curve, I guess, of this 3 and starts breaking it down into its components. Okay, I understand this component of a 3. I understand, let me change colors so it's easier. I understand this component of a 3. I understand this component of a 3. I understand this. It then pieces together each of these curves. It starts to understand each component of the 3 until it can classify that, okay, this is a 3. Because, for example, the human body, how it works, right? We have this 3, this 3, that's not a 3. This 3, we, even though they're different in a way, it's, we can still process it that, oh yeah, this is a 3. Even if our 3 looks like this, it's a 3, right? Our human brain can understand it. That's how neural networks understand, because we're looking at certain key points. We're looking at, okay, does it have this curve? Okay, it has this curve. Does it have this curve? Okay, it has that curve. Okay, does it have this curve? Bam, it's a 3. So that's how neural networks also process information as well. Okay, so um, we have 144 neurons over here. Each pixel gets its own, neuron in the input layer. So we have 1, 2, 133, blah 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 blah, 144. Okay, there's 144 of them because that's our input layer. And then the output layer predicts the final outcome. So let's say we're predicting between 3 and 5. Okay, that's how this would work. After looking at the activations, looking at each angle, curve, whatever, it's gonna look and see the probability that it's 3 or 5. That's how it works. Then we go into our middle layers, which is our hidden networks. And how much, hold on, how much the system thinks the given image has the probability of being that number. That's what this is. All it is, for example, if I give it an image of a 5, it would say, okay, there's an 80% probability that it's a 5. There's a 20% chance of it being a 3. That's all the output layer would tell you. Okay. So now, based on the image, different neurons are activated in the hidden network. So if you notice, we have some activated layers here. We have some activated neurons in the layer. And then here we have, for another number 5, we have some other activated ones. So based on the image, it activates different things. And these activations represent different curves that it broke it down to. For example, this could be this curve right here. This could be this curve right here. But this could be the curve of a 3, right? So that's why it's not activated. This could be, the bottom thing could be the curve of the 3, right? So that's kind of how this works. After it checks that, okay, yeah, that matches, this matches, it then looks at the other types of possibilities that it can come, right? Then it checks, okay, does this match? No, it doesn't match. Okay, we're not going to go to that. Based on these activated neurons, it then makes a prediction. Okay. Next up, we have a question. Okay, so how that works, right? The color being turned into a value of 0 and 1. What it does is it takes, let's take this image right here. It converts this all into black and white. Okay, all this turns into black and white. After that, it's taking the pixels and then it assigns it a grayscale value. So if it's black, completely black, it's going to be 0. If it's completely white, it would be 1. If it's something in between, the computer knows, like, okay, it's around 0.2 because it's more black. It's around 0.9 because it's more white. It's not perfectly white, but it's close to white. The computer can knows that value. That's how that works. Okay. So now in deep learning and neural networks, how this works is that we first convert this image right here into the grayscale, understand the raw pixels, right? We're understanding each one of these neurons in this, okay? And in the early layers, so we have our neural network with our input layers, and then in the early layers, usually in the first, depending on how big your neural network is, um, in the early layers, you're understanding the curves of the image. So you're understanding, okay, there's a curve right here. Okay, there's a curve right here. Okay, there's a curve right here. Okay, there's another curve. Okay, it's understanding all the curves. In the middle layers, you start to understand your objects or parts of the object. So, for example, you'll understand this eye, this mouth here. You start to understand that. And then here, we have a question. So AI is colorblind. Mm, kind of, mm, kind of, I would say. Not really, because it can distinguish between the color yellow and green. How does it do it? It turns the color into this grayscale value and reads it, because obviously yellow has some other grayscale value compared to green, right? It's not going to be the same thing. It's not just how humans perceive it, because I'm sure that it's going to be hard for us to tell the difference between yellow and green without prior knowledge. But the computer knows, okay, yeah, I can see that yellow is, I'm just making this up, is 0.8 and green is 0. I don't know, 7. So now, okay, this is yellow and this is green. That's how it understands that. That's how that works. Okay. So the network breaks down the two types of images into the components, and for each neuron represents a different component it activates based on the similarity. So what that basically means is basically what I explained before. It understands the two images and then it breaks down the image into its components like before, understands the curves, blah blah blah, then compiles this data set and then it activates those different neurons based on the similarities. So that's how that works. Okay. Neurons are connected to the next layer through things called channels. So we have a channel, and how we can calculate these things is through things called weights. So what a neural network does is initially assigns a weight, a randomized weight for each of these channels. So we have our input value, right, of our pixels of the image. This case, this was from a previous example that I created 2 days ago. Distinguish between a square or circle. So it takes the neurons or the input pixels of this, and then it feeds that value through a weight. So in this case, we're calculating the bias for this. Okay. Um, what we're doing is we're doing x1 times 0.4 plus x2 times 0.6. So that's the weight of this channel, 0.4, and 0.6 is the weight of this channel. You see how we're getting this weights here? And then we're adding in the bias that's already set here, and we're calculating it. So initially, all of these values are random except for obviously the neurons here, the input neurons, because those are already given by the grayscale values, right? Um, but all of them are random. I'll go more into how we're getting a optimized output, but initially your neural network is going to be completely random and it's going to be completely inaccurate. Okay, so after doing this calculation, what it does is it feeds it through an activation function. So a couple of activation functions out there are like ReLU, which is really common. Also sigmoid function, the function we use for the logistic regression model. So it's did I go back a page? The logistic regression model. Basically, the curve looks like this, and basically, it's just a linear curve that's smushed to fit in between a 0 and 1 interval. Because what are these neurons between? 0 and 1, right? That's the grayscale values of. um, seeing, okay, what's the activation based off of, right? So what it does, it takes in our input data, our linear input data, right? And then it's being all the calculations we did before is being fed into the sigmoid function, and then it's being smushed into this sigmoid curve between the values of 0 and 1. So that's how each of these works here, right? Then it's creating the activation number, and then we're checking based on the input data we give it. For example, it's a square. We're checking, okay, should this be activated or not? Based on the value, if it's a high value close to 1, of course it's going to be activated, so it goes on to the next step, check through the channel. So it looks at the channels that it's connected to, and it does the same thing. So it runs thousands and millions of these processes like this. Okay, on to the next step. Okay. Okay, in this case, since the output is wrong, let's just assume that this was 0.2 and this was 0.8. It's going to keep doing this again. It's going to do back propagation. I'll get more into that in 1 second. So, since in the beginning all the values are random, the model needs to improve itself because obviously this output, the output could be wrong, right? Because obviously it's random values, so it's most likely going to be wrong. So what we can do is calculate this thing called cost. So let's take this 3 input data, right? And let's say the model predicted as 40% chance that it's a 3 and 60% chance that it's a 5. Obviously, since it's a 3, it should be higher than 40%, right? So that's wrong because the actual result would be what? It would be 1. And since the actual result of this input data would be 0 for 5, we need to calculate how much we were wrong by. So what we do is calculate this thing called cost. And all cost is, it's a very simple formula. All we do is we get the summation, we get the summation of our prediction, okay, P, minus our actual squared, okay? So in this case, we have 0.4 minus the actual, which is 1, squared plus 0.6, which is the prediction, minus 0, and squared. And that's negative 0.84. Now this tells our model, okay, we need to improve somewhere. Because what would be a perfect model, right? Let's think about it. What would be a perfect model? 1 minus 1, 0, 0 squared is 0, right? 0 minus 0 is 0, 0 squared is 0, right? And then 0 plus 0 is what? 0. So the ultimate goal of the model is to reduce this cost function as much as possible and as close to 0 as possible. That's what we're trying to do. The end result is needs to be as close to 0 as possible. We need to minimize that error. But how does that work? Now that the model knows it's off by such a high magnitude, how does it adjust itself? Well, it uses this thing called back propagation. Backpropagation looks at these values that need to be adjusted upwards or downwards and changes the weight to match that. It looks at this uh, right here. So as you can see, this needs to go upwards a little bit, and this needs to go downwards. And then what it does is it goes back in the model. So let me go back a couple of slides. So then forward propagation is where it does that calculation, remember. So I'm just going to say x1 times weight 1 plus x2 times weight 2 plus the bias, right? It's going to, forward propagation is where it does this and goes forward until we get to the output. Back propagation is where now it needs to fix itself. It needs to go backwards, optimize those values. Now that it understands what it needs to change it by, it then, so that's the gradient. The back propagation gives its gradient, and we can use functions like atom or gradient descent to now optimize the weights, because remember in the beginning all these weights are what? Random. So now atom goes on here, or gradient descent, and what it does is it tweaks the weights. It then adjusts these weights to the magnitude it was wrong by, right? So let's say it now the weights need to go higher because that's what the model is saying. It's gonna go, okay, a little bit higher. Let's try that. It's gonna run it again through forward propagation. And then, okay, it looks like there's an error, it needs to go down a little bit. Then it goes back, atom goes, performs the weights again, optimizes the weights. It goes down a little bit this time. It keeps doing this cycle back and forth until either the number of trials you set is gone, or if you have like a GPU optimizer, you can't improve your model any further, then it's just going to stop the model. Um, so that's how neural networks work. Does anyone have any questions before we go to the coding stage? I'll get more onto max pooling in a second, but anyone have any doubts so far? No doubts? Okay. All right, so let's go onto the code. I'll explain max pooling once we do the code because it'll make more sense then. Give me 1 second, everyone. Can you guys all see the code yet? Are you guys able to see it? Oh yeah, no worries. Yeah, okay. Let me share my screen again. Give me 1 second. I need to stop recording. Okay, so basically, what I did was I created a data set that I got from Kaggle, and it has images of happy people and sad people. And the goal of this data set is to predict whether the person is happy or sad. So I just reran the model because I forgot to change the path of this, because I was having some issues before with some other data sets. But let me explain how the code works. Oh, yeah, you guys can see now. Remember how I said all the weights in the beginning are totally random? Well, you can tell that by the results as well. Look at the results. Look how low that is. That's super low, right? And now it's starting to improve itself. It's trying out new weights using the optimizers, right? It's getting higher and higher the more trials. So I set 10 trials because I don't want this to take too long. But usually a lot of people set like hundreds of trials, right? To get like a higher result. Sometimes it's not the best thing because it kills your GPU and stuff like that. That's why I use a GPU optimizer. But yeah, if you notice, I have an accuracy now of close to 90% already. But yeah, that's kind of how you see the model train itself in real time, which is pretty cool. I just want to see what the end result is. Okay, nice. And did you guys notice it's not always going higher? Here it went lower from last time, and it improved itself and got a higher accuracy. But yeah, let me explain the code first. Okay, so here I'm importing TensorFlow, so that's a library that holds all these neural network stuff, machine learning stuff, right? I'm getting the stuff from TensorFlow, all the models, and then from TensorFlow and Keras, I'm getting this specific thing called pre-processing. Pre-processing is basically a stage you do before the data, inputting the data. And in my case, what I did for my pre-processing is I use this image data generator. And what it does is it scales all my images to a certain size. In this case, I'm doing 255 by 255 pixels. Okay, so 255 by 255 pixels means how many neurons in total for that first input layer? Who wants to do some math real quick? Anyone have their calculator on them? Let's see. Yeah, good job, Ritvik. So 65,025. Okay, so that's how many neurons we have in the first layer. So we have one, two, skip a few, then we have 65,024, and then 65,025, right? Bam. That's how many layers we have in our input. Then, it breaks off into branches, blah, blah, blah. Okay. Let me delete this stuff.
Okay. Computer auto generates the middle layers.
Good question.
How runs in the middle layers? Like,
yeah, let me get to that part. It's over here. I'll explain it in a second. Okay, here we have the train data. So remember, in our other machine learning projects, train data, and we didn't split the train data and validation data and stuff like that before. Now for neural networks, it's very important to have a trained data set where because remember what a neural network does, right? It cross checks, right? It cross checks. Okay, we have our training data and we have our validation data, and it does a cross check. That's how it works, right? So we need to have these two separate data sets here, and that's all I'm doing is just giving the data and setting it as trained data. That's it. Nothing too complicated here. Um, okay. Then here, also this all this means class one binary. That means there's two images in there. So inside of data, there's happy and sad. That's it. Um, okay. Here is where we're actually creating our model. So this is where the layers come in. So as you can see, there's a couple of layers in here. We have our first layer, right? Our first hidden network, and then we're using an activation ReLU, right? I was teaching guys sigmoid function, but this one I'm gonna set as ReLU, okay? And then I'm creating the input shape, right? I'm setting the size of this, and then the size of the pixels. Actually, sorry, not 255 by 255. I set it as 64 by 64. That's the input shape of the images we're feeding in. So I'm scaling them all to a certain size, right? And then here we're just building the model, right? How many neurons we want to have in that layer, stuff like that. And then here is max pooling. So going back to max pooling, what it does is, okay, let me draw it out. So let's say we have this over here. Okay. Let me see if I'm missing something. Okay. Okay, that's fine. All right. So let's say this has a value of 3, 4, 5, 6. Okay. Let's say this has a value of 7, 8, 9, 1. Let's say this is 1, 3, 5, 7. Let's say this is 2, 5, 6, 7. And what max pooling does, it takes this highly complex image and then it simplifies it for the next layer. What it does is then I'm created a 2 by 2 pixel, so it looks at 2 by 2 pixels at a time. So let's say it starts up here, right? That's 2, 1, 2, 1, 2, 2 by 2, right? Then it checks the highest value. It takes this value. Now it's going to put it here, 6, okay? Then it checks the next one. Okay, 9 is the highest. Then it puts 9. Then it checks this. It takes 7, puts 7. Then it checks here, takes another 7. Now what it did was it broke down this highly complex image into its most important features. Its most important features, right? That way, the model can now understand on a high level what I'm looking at. Then it gets more specific and stuff like that, right? So now it's trying to understand the image on a high level. That's what max pooling does. Okay, next. Here, creating another layer, right? Setting the amount, how big we want it. Then checking our activation. We don't need to input anything anymore because it's already inputted, right? Then just like that, we're doing this again. Then we're flattening it. What this means, it's taking our two-dimensional data, right? And then it's basically squishing it, and converting it into a one-dimensional data. That's all it's doing. Then here, that's all just the sigmoid function stuff here for the activation. Okay. So now here, I'm actually, compiling the model. I'm using the optimizer atom, and for my metrics, I'm using accuracy. I can also use some other metrics, but accuracy, it's pretty useful in this case. Then I'm using my loss function. Remember, we use mean squared error, but in this case, I'm using binary cross entropy for a loss function. And then I'm finally fitting the model, which means I'm training the model, right? And I'm training it on the trained data, and then I'm giving it the validation data, and I'm setting it to validation data, and then I'm setting the amount of trials I want. I could also set this to a very high number, like whatever that number is, right? But just for this training purposes, I'm saying it's here. But also, the amount of trials don't necessarily mean a better output, right? You could have like 50 trials and all the results be almost the same thing, and you're just wasting time, GPU resources, computation power, and different things like that. But yeah, that's how this works. Any questions on this? Anyone have any questions? Okay. All right, so what we'll be doing is I'm going to be providing you guys this code, but I want you guys to all look for directories of your own images. You can just use this code, right? Change your directory, and inside that directory, have two folders with separate names. Okay, we're going to work with binary classifiers for now. And then what you're going to do is get those two data sets that you compiled through Kaggle or just downloading data off the internet. You can grab the data and then use it to train this model. Okay, so I'll put the code in the Discord like always, and I'll make sure to push all the code to GitHub after this class. But let's go there. Okay, you guys can take that code that I created, and I'll give you guys the rest of class time to explore with it, and I'll give you most of class time tomorrow, and we're gonna do presentations. So yeah. Also, tomorrow is gonna be a little bit of a fun day, so I'm gonna have some activities planned out for tomorrow. Okay. Yeah. Thank you, everyone. I'll give you guys the rest of the time to work on that. If you have any questions, please reach out. Okay. All right. So, who wants to go first on their presentation today? Anyone want to volunteer to go first? How many people actually finished their presentation, or do you guys still need more time? So the presentation we're doing today is. Can you put the videos? Yeah, it's still exporting from my computer. I was doing it earlier today on the video. But the presentation is we're creating a neural network and on two data sets, and we're just trying to predict the differences between that. Yeah. Okay, I'll do this then. I'll give you guys some time to work on that, and then I'll give you guys maybe 15 minutes to work on that, and then when we come back, we'll start with presentations. Okay. Um, I guess I'll present first what I've made because I'm also going to be presenting. So yesterday I did for our example, the sad and happy face like differentiation model that basically just like predicted whether it was a smiling person or a sad person. So today what I did was a little bit different. So I downloaded two data sets, and one of the data sets was of the basketball player LeBron James. So I downloaded that data set. And then I also had a data set that I downloaded with pictures of Kobe Bryant. And my model's goal was to predict between um, like Kobe Bryant and LeBron James. So basically, if you guys remember from the classes I had on neural networks, initially neural networks, how they work is I'm first scaling all the data into one size, right? So in this case I'm doing 64 by 64. That's the input size I'm giving the model. So what does that mean? Who wants to just tell me what 64 times 64 is? Anyone have their calculator?
4096.
4096. Okay. So that means that there's 4096 neurons in our first layer, right? In our input layer. So that means 1, 2, skip a few, 4096. Okay. Yeah, thank you. All right. So that's our input layer, right? Then how does this work, right? Who can tell me how the channels weights are coming from in the beginning? How are the weights created? Are they is there a specific number in the beginning or no? In the beginning, the weights for this model. I'll give you guys a hint. Look at the results in the beginning. Look how off that is. 45% accuracy. Are the weights in the beginning, are they structured in some way or are they random? Which one is it?
They're random?
Yeah, they're random. That's backpropagation. Backpropagation, yeah, would be after like optimizing. It would be part of the optimization process. I'll get more into that in a second. It'll be like a quick refresher on what we did. Yeah, so then the weights initially are random, right? So we have our input, right? X1, X2, then we multiply it by the weights and then add the bias. And then that's what we get for this cell, right? And then we apply our activation function. So in this case, I'm using ReLU, or you can also use sigmoid, right? Sigmoid and ReLU, all they do is just create a function that can be compressed into the values of 0 and 1. 1 being fully activated, 0 being not activated. If you guys remember how the process works, we get our image, convert it into a grayscale value, and then all the pixels are now the neurons in the input layer. So far, that's how this model kind of works right now. After getting that result right, it then calculates the cost of the function, right? All the cost is your summation of the difference between the actual, your prediction minus the actual squared, right? So since I have 2, then I would just add prediction of LeBron James plus prediction of Kobe Bryant squared, right? See what the cost is. So in the beginning, right, we had a 45% accuracy. That means there was a very high cost. The goal of the cost is to get as close to possible as 0. It needs to approach 0. So since there was a very high cost, that means low accuracy. The model then uses optimizers like Atom or gradient descent to uh, it would use optimizers like gradient descent to do back propagation. So what back propagation does after you build the network, right? Blah blah blah. You build your network, you get these complicated outputs, and then it leaves you with 2 outputs over here. So what back propagation then does is then it goes backwards, right? It sees the magnitude of how much it was wrong by, and then it adjusts the values. It looks at each one and says, okay, this needs to go up a little bit, this needs to go down. And then when it back propagates, it gives the gradients to the optimizers. So the optimizers then come in like Atom or gradient descent, then optimize specific weights. Now these weights are changed based on what the gradients the back propagation gave it. So now they're tweaked a little bit. Let's say this value needs to go up a little bit. The weights here will go up. That's how that works. Okay. Yeah, so here I'm creating my training data and my validation data set, right? Feeding in the target size of 64 by 64, binary because it's uh, two classes, right? It's not multiple. I'm just predicting between 2 things. And then I'm setting the directory. That's just basketball. Okay, and then I'm setting whether it's training or validation. Okay. And then we have a 20% validation split. Here, you're actually creating the model. So I explained most of this yesterday. We're creating the different layers here. So that's a layer, that's a layer, and then we're flattening it. So we're transforming our 2-dimensional data into 1D where the computer can understand it. And then we're creating our dense functions with our activation. So this is our 2 outputs that we're creating here, our output layer. That's what we're creating over here. Okay. Here I'm finally compiling the model and then I'm training the model with the data set. And then as you can see, accuracy is very low in the beginning because why? It's using random weights in the beginning. So it's not accurate. And then the more it trains, it starts getting more and more accurate. And then we had an accuracy of 90%. And here I'm just testing it out. But unfortunately, my kernel keeps crashing. I think it's using too much resources right now. I have a lot of stuff running. But all I'm doing is setting some example path from whatever data set I got here. And then I'm just feeding it into my model that I created. And then giving a prediction. That's it. Yeah. Okay. So that was mine. Does everyone understand how neural networks work now? The basics of it? Okay. Nice. All right. Who wants to go next on their speeches or their presentations? Anyone else want to go? Oh, also, guys, I will be giving out certifications to whoever participated. So give those out soon after this. And right now, all the videos are being imported into YouTube. So you'll have all the videos, all the resources. I'll put everything back. It'll just be a certificate of participation. Yeah. Okay, who wants to go next for their presentation? Anyone want to go first? Okay, if you guys didn't finish, right, what you can do is just do a presentation or just like, unmute and talk about what you learned in the neural networks, like what you understand from it. It doesn't have to be perfect, but just try to explain what a neural network is, and then I'll see if you guys are understanding it correctly. Oh, you want to present, Ritvik? Oh, yeah, go ahead.
I can't really present because my code's kind of bugging because thing doesn't want to generate, I guess.
Oh, yeah. The error from yesterday. I honestly don't know why your computer's doing that. Did you try adding your Python to Path? Because that should fix it if you added it to Path.
I have no idea how to do that, and I was like a little busy yesterday.
Oh, okay.
So yeah, I'm just gonna explain how neural networks. So neural networks are a type of AI which takes a picture and takes it in the output. It's kind of like decision trees, except there's more going on in the middle. So first, it takes the picture and it breaks it down into a grayscale, right? So if it's color, it turns it into a grayscale and then sets it on an actual scale of 0 to 1. Then based on that, you can look at basic patterns. Then the middle processing neurons helps the output layer make a probability of what the number prob- it processes the different patterns and, and helps it figure out what the actual shapes are, and then based on that it'll figure out if it's one or another. But the reason how the neurons are connected is through channels where the data is randomly chosen through which channels it goes. Those, and at the very end, will check for accuracy. If it has high accuracy, it'll keep the channel weights that are generated randomly. But if it's not, then it won't, and we'll just switch it up again until it tries to get the right one. The formula for checking the accuracy is called the cost function, and the goal is to try to get as close to zero. So it's prediction one plus the right answer to square root plus prediction two plus the wrong answer squared plus bias. And if that is zero, then you got literally perfect. And they also use back and front propagation to optimize the models with the weights and stuff. Yeah.
Okay. Um, yeah, for the most part, you were correct. Let me just clarify on the ending a little bit. So we use the cost function, right? So each trial the model runs, it goes through, the different combinations of weights, and the cost function says how much those weights like corresponded to that value. So, for example, you had some random weights, right, and it said that you had a value of negative 0.9. Well, obviously that's very inaccurate, right? Um, so then it checks the magnitude and changes the weights by that much using back propagation, which gets the gradients, right? And then it uses an optimizer to actually optimize the weights. So that's the only thing that was I just wanted to clear up. But yeah, good job. Anyone else want to go? You guys can also present about other things, not just neural networks. That's easier. Anyone want to go? Okay. How about we do this? I'm gonna randomly select someone, and I'll ask them to do a presentation. Um, let's see. Okay. Padma, do you have any? Do you want to explain what neural networks are, or do you want to give like a presentation on a project you worked on this week or this workshop? I guess. Yeah, it can just be like explaining what neural networks are, or if you created your neural network, like the project yesterday, and then, or it could be like whatever project you worked on before, like logistic regression, linear regression, decision trees, KNN, stuff like that. I mean, it would be good if you go now because I'm gonna keep selecting someone because today was supposed to be presentation day of what we've learned so far. I mean, it doesn't have to be perfect. So if you want to go, yeah. So I just don't want to review. It could be anything. It doesn't have to be CNN. It could also be linear regression, something like that. But I understand. Does anyone else want to go? It could be on anything we learned this week or these 3 weeks. Yeah, sure. That's okay.
Okay, I'll share my screen.
Okay.
Okay, so this is a decision tree I made a while ago. I used this data for the grades of students, the sleep hours, and their daily usage of social media. This part over here trains the model, and this is the decision tree that was created out of it.
Okay. Can you explain like what each leaf means?
Yeah. So the first leaf is sleep hours. It has the lowest germanium purity, and it breaks it down so it can create leaves with leaves that are pure. So it breaks down. This is the grade and sleep hours, the daily usage, and these are the pure leaves at the end.
Okay, yeah, that's good. Can you go up to your code again? Let me see. Okay, steps, create the data space. Okay, yeah. All right. Do you know how to import in a database? Do you have any projects where you imported in a
Oh, yeah.
database from? Okay, yeah,
Like this one.
yeah. Go ahead and explain this one,
Okay.
and tell
I
me
think I
where you
already
got the.
presented this one.
Yeah. Just like explain
Yeah.
the part on how you imported in the database and how you like brought it into the code, because you also
Okay,
use like a
so
label encoder. So I want you to like talk about that as well.
okay. So I went into Kaggle to get the data set. I downloaded it and I dragged it into the side over here.
Yeah.
And then I opened it.
Mhm.
And over here I put read CSV and put the name of the file to import the data.
Okay. Yeah. All right. Thank you. Yeah, that was good.
Okay.
All right. Okay. If anyone else wants to present, you guys just unmute and present. Um, I want to talk about one more thing before we end this call. But does anyone else want to present on what they learned? Because this would be pretty sure it's our last class, right? Yeah, pretty sure. So does anyone else want to present before I talk about my next thing? Okay. I guess that's fun. All right. So I wanted to talk about some opportunities that you can do through AI, machine learning, and things like that. Um, so basically, I'm sure all of you or some of you might have heard of competitions like ISF, right? It's basically a science and engineering fair, and you learn a lot from it, really. So basically, you can apply AI. Have you ever been to ISF? I've been to Texas F. I placed at regionals and went to Texas, but I didn't go to ISF. Yeah, yeah. Thanks. So ISF, but you did the yeah. I went to Tokyo to present at Tokyo University on my cancer research project. Yeah. Um. So basically, yeah, no worries. So basically, ISF is a science and engineering fair that you can do, and you can just select any research topic and do it. And AI and machine learning is a very great topic to use. Like my project was, I predicted 7 types of cancers through neural networks. I created I think 6 different types of neural networks, and I also discovered well, 2 new biomarkers through genetic data. So I did like genetic processing and stuff like that. But uh, ISF, it'll help you understand more on AI. Even if you don't win, you'll get more knowledge into like what research is, and I think that's a really great opportunity for students to have. It also looks really good on colleges. Like if you ever been to like ISF, that's like a big deal, right? It looks really good, and if you start any research on your own, that's also a big thing. Just qualifying to ISF is a big deal. The international thing, it's a big deal. State itself is pretty big, but going to internationals is even bigger. So how it works, right? You have to get like first in your like category, and then you have to place some placement in the entire competition. So everyone who got first in their category goes to a separate event, and then they have to compete. That's how that works. So a lot of cool things happen in ISF. I seen a guy use a wheelchair and he controlled it with his brain. So the brain was giving signals on where the wheelchair should move. So it was a really good experience. You learn a lot about research. A couple of other competitions is the Congressional App Challenge. The Congressional App Challenge is basically a app competition where you can develop apps towards your congressional district, and just like I don't know, you can either talk to whoever runs your district and see what type of apps they're looking for, or just develop an application you think that's a need in the community. So I think 2 years back I created a health, mental health and OCD management app, and this last year I created like a carbon emission AI calculator app that basically tracks your carbon emissions, runs statistical analysis, and gives you AI recommended feedback based on your data. I created a couple of apps like this for this challenge, but I think that's also a really good opportunity, and AI and machine learning definitely look really good in this. For uh, I mean, I could probably find the deadlines and send it to you guys, but your best bet. I sent some resources in the in an email to everyone that signed up for the class. I can also put the resources in Discord, but those have all the information on deadlines, what to submit, more information. I'm just giving just kind of an overview of the different competitions that are out there that could boost your resume. Let me think. So I said ISF, congressional app. So there's a lot of different competitions like this. Let me check the email. I know there's a couple more stuff that you can do. Okay, so So have these. I'm gonna put the links in the Discord real quick. Okay. So I sent the resources in the Discord for the congressional app and the ISF. So depending on where you guys are located and your school districts, um, it would work that way. But I'm pretty sure for ISF, you have there's a school fair first. So I would talk to your counselor or whoever manages all the clubs and stuff. Ask them about ISF and the science and engineering fair, and they'll give you details because there's usually how it works is that there's a local fair, right? There's a local science and engineering fair before you go into regionals. So usually that's held by your school. Just ask if your school does that, and if your school doesn't have anything like that, you would need to ask like a teacher to sponsor you to like do ISF at regionals. Or you can have your parents. I think you can also do it with your parents. Um, but I'm sure your school would give you all the resources after you like win. So you have to first win your local fair before going on to regionals, and then after regionals you would get selected for state, and then you would go into internationals. That's how that works. Okay. Does anyone have any questions about these types of competitions right now? Okay. Anyone other ones? I'll drop more resources in the chat once I think of other competitions that you can use AI for. There's a couple more, but I'll drop them in the Discord once I get the chance. Yeah, but anyone have? Oh yeah, I wanted to do this as well. Anyone have any ideas that they want to pursue after this workshop? Like, you know, creating a specific AI model for something or something like that. Does anyone have any ideas? It's okay if you don't. I'm just kind of throwing it out. Yeah, today's the last day. Yeah, yeah. All right. So what I want everyone to do is, if you guys can get on your cameras. We're gonna do like a picture for the last day. So let me see if I can. How do I do this to camera? Okay. If you guys can turn on your cameras. Okay. Okay, that's fine, Dia. Okay, that's fine. All right, cool. It's nice to see everyone's faces. All right, we'll take one picture. So whoever can turn on their camera, I'll give you guys like a minute. So 5:54. Okay. Okay. All right. We'll take a picture. So everyone just smile. Okay. I got the picture. All right. Thank you guys for joining. That's all. If you guys have any other questions, I'll be posting all the resources shortly. All the videos will be posted. Um, so once I finish recording this one, I'm gonna post all the videos, all the resources that we have. If you guys have any questions, yeah, no worries, Sanjana. Thank you for joining. If you have any questions, I'm always available on the Discord. You can reach out, ask questions, and yeah, feel free to join me for our next sessions. And yeah, thank you all for joining. Bye, guys.
Thank you.
Yeah, no worries, guys. Thank you for joining. Yeah, no worries. Thank you, guys.
Thanks. Bye.
Yeah, bye.
Thank you.
Yeah.
Thank you.
Yeah, no worries. Bye.